Hi everybody, and thank you for watching this Unit 2 video where I'll show you how to calculate the average atomic mass of an element from percent abundance data. Now, before we do this for real and take a look at the calculation, let's just remember some things that we've looked at recently in class. First of all, the idea that not all atoms of a given element are the same. Let's take carbon for example. Carbon comes in three naturally occurring types: carbon with a mass of 12, carbon with a mass of 13, and carbon with a mass of 14. Every single one of these carbon atoms has 6 protons. Protons are what make these atoms the element carbon. If they didn't have 6 protons, they wouldn't be carbon. What gives them the different masses is the fact that this carbon has 6 neutrons, this one has 7, and this one has 8. We of course call these isotopes. Now when you look at carbon on the periodic table, you'll see two numbers. One of them is 6. That's of course the atomic number. It's a nice whole number 6 because carbon is always 6. That never changes. The confusing part on the periodic table is that the mass is given as a decimal, 12.011. Now it's not possible to have 0.011 of a proton or of a neutron, so sometimes it's confusing where this decimal comes from. The reason that decimal is there is because periodic tables give you the average mass of all carbon atoms. So, like we just saw, carbon can have a mass of 12, 13, or 14. So on the periodic table, the decimal you see is the average mass of all those different masses combined. And that's what I'm going to show you how to calculate in this video. Now before I show you how to do the actual calculation part, let's take a look at one more piece of information you need to be familiar with, and that's this idea of percent abundances. A percent abundance simply shows how common or abundant each isotope is. Carbon-12, for example, on the left has a percent abundance of 98.9%. That means of all the naturally occurring carbon atoms, 98.9% of those carbons are carbon with a mass of 12. Carbon-13's is only 1.1%, and carbon-14's is extremely small, less than 0.001%. What you could say from these numbers is that carbon-14 is the least abundant isotope out of the three, because very little of all the carbon atoms exist as this type, whereas carbon-12 is the most common or most abundant because almost 100% of all the carbon atoms you'll find are carbon-12. Now we can actually take a look at how to do the actual calculation of an average atomic mass. One more quick thing though before we do that. If you're sitting there saying, I already know how to take an average, you just add up all three masses, 12 plus 13 plus 14, and divide by 3, you'd be wrong because we have to do a special type of average here. Since each isotope has its own unique percent abundance, we have to use a special type of average called a weighted average that takes into account the fact that most of the carbon atoms are carbon-12 and very few of them are carbon-13 and 14. So here's how you do a weighted average. I'm going to show you two examples. The first one I'll do nice and slow so you can follow along. The second one we'll do a little bit faster. The problem's going to give you information that pretty much mirrors this every time. This is about copper. Copper has two common isotopes, copper-63 and copper-65. Copper-63 has a percent abundance of 69.09%, while copper-65 has a percent abundance of 30.91%. And the question is very simple: calculate the average atomic mass. So the first thing you do is take all the different masses of all the different isotopes you have, and I just like to write them out in a vertical line. In this case, it's nice and easy. We only have two isotopes, 63 and 65, so you just list them like that. You're going to take each of those masses and multiply them by the percentage, the corresponding percentage. But before you do that, you're going to move the decimal place in the percent 2 places to the left. So since copper-63 has a percent abundance of 69%, I'm going to multiply 63 by that percentage, but with the decimal to the left. So 0.690 and 9. And you'll do the same thing with the 65, multiply it by 30.91%, just with that decimal place moved 2 to the left. So 0.309 and 1. When you're done with that, you multiply through and get your answers. So when you multiply, these are the numbers you get, 43.527 and 20.092. Now there's one final step, and that's the benefit of writing these in the lines the way I've shown you. You take the answers from the multiplication, draw a big line beneath them, and get the final average by adding all of those numbers together. And in this example, after you add those two numbers, you get 63.62. That is the final answer and is the average atomic mass of copper. Now I'm going to show you just one more example. It's a little bit more complicated because in this example there's three different isotopes, magnesium 24, 25, and 26, each with their own percent abundance. A good idea is to pause the video now and try this on your own and then check your answer as we go over it, so you can see how you did after just looking at how to do this one time. Now that you've had a chance to try this, let's check your answers with the proper answers. First thing you should do is line up the masses, 24, 25, and 26. Multiply each mass by the percentage, but with the decimal place moved 2 places to the left. Get those answers. Those are the three numbers you should get. Final step is add those three numbers together for a final average atomic mass of 24.46. That actually concludes this video on calculating average atomic masses. Please enjoy the recap to follow.